This is the last lesson in Unit 5 on optimization. Optimization is a really common application in calculus, used in business and almost every other industry when we want to find the least amount of time or the greatest profit or the shortest distance, maximum volume, minimize waste, all kinds of interesting concepts that go on in our world. Students find it challenging sometimes because of finding what quantity needs to optimize or the constraints, and then how to write the equations for what they want to find the derivative for. So let's begin with something pretty straightforward. Let's say you have two positive numbers, and the sum of the first and twice the second is 64. So we want to establish x is our first number and y is our second number, and write an equation for that first sentence. Y is the second number. And then we can write an equation. So the sum of the first and twice the second number is 64. And then if I thought about that as just the end of one thought, we've taken care of that part of the problem. Then the product is the next part. We want to maximize the product. So here's the difficult part. What thing has to be maximized and how do we go about setting that up? So the product is a maximum. So we have x times y, and we want that to be a maximum. So we have two equations. One's called a primary equation, one's called a secondary equation. If I take this equation and solve for y, I can substitute that over here in this equation, and we could call this a function f of x. So let's do that. If we had 64 minus x divided by 2, that's a name for y, and I could say I want f of x is x times y. I want it to just be in terms of x. So we could substitute 64 minus x over 2 in place of the y in our function that needs to be maximized. So to find a maximum, I want to take the derivative and find where the derivative is 0 and test those critical points. So this is the big idea. How do you get a maximum? Find the derivative. So first we'll clean up this a little bit, have that distribute that x, 64 minus x squared, and we got half of that. So f prime, f of x is half of 64, that's 32x minus a half x squared. Now we can take a derivative. So f prime of x is 32 minus x, and x is 32. Now you could make a sign chart, check the derivative, substituting a number in here. We have positive, and a number in here on the other side of 32. We have negative. That's a maximum, but normally this is going to work out no matter what. So if x is 32, then to solve for y, we would just go back and back substitute in here. 64 minus 32 divided by 6 would give us our y. So y is 64 minus 32 divided by 2. That's half of 32, so 16. That tells us the two numbers whose product is a maximum are 16 and 32. 32 is the first number, 16 is the second number. That was pretty easy. So moving on, you have a farmer plans to fence a rectangular pasture against the river. So here's the river. We're going to make a rectangular pasture to keep all of his horses and chickens and things. And the pasture is going to have 180,000 square meters to provide enough grass for his herd, so it must be for cows. What dimensions would require the least amount of fencing if no fencing is needed on the river? Well, we have some fencing here, we'll call that X, and some fencing here and here, that we'll call that Y. So we know that the domain is that X has to be positive. We can't have any negative values of X. And we know two things. We know that the area is X times Y, and we know the perimeter is X plus 2Y. What else do we know? We know the area is 180,000 square meters, so A is X times Y because A is 180 square meters. Okay, solving this for Y is 180,000 divided by X. And if we wanted to take the second equation, the perimeter equation, and write it in terms of just X, when we have X plus 2Y, we've just renamed Y. That could be substituted in for the variable Y here. We'll give that a try. Perimeter in terms of X is X plus 180,000 divided by X. So let's see. Oh, wait, it's 2Y, isn't it? Missed that. So the perimeter in terms of X is X plus 360,000 divided by X. And we're wanting to use the least amount of fencing. That's perimeter. This is what we're maximizing, or minimizing the perimeter. So the perimeter derivative is 1 minus 360,000 over X squared. If you set that equal to 0 and solve for the critical number, then 1 is equal to 360,000 divided by X squared. So X is the square root of 360,000. Which is either positive or negative 600 meters, but we know it can't be negative because the domain has to be greater than 0. So here is the X dimension. This is going to be 600. And if we substitute in here, when X is 600, what's Y? Y is 180,000 divided by 600. So 6 into 1800. Y is 300 meters. X is 600 meters. And putting that all together at the end, we could say the pasture measures 300 meters on the sides by 600 meters parallel to the river. Now, one thing I didn't do is I didn't do a first derivative test. But if you go back and figure that out, starting at 0 here, you have negative, positive, our critical number, decreasing, increasing, and a minimum value. So we minimized the amount of fencing needed by the farmer. Okay, let's go to a little bit more difficult one. Let's say you have an open box that's being constructed from a piece of sheet metal, and the sheet metal measures 18 inches by 30 inches, And we want to cut out a little square from each corner of equal size. So these are X by X on each side to be able to fold those sides up and make a box, right? So our box is going to look like this. You take that sheet metal, you cut out these squares, throw those away. They're X by X. Fold up the sides, we're going to get a cardboard box or a sheet metal box that looks like that. Excuse me. Next, we need to figure out the volume because we want to know what size squares should be cut out to make a box that has a maximum volume. We're looking for the size of the squares. We want to know what X is. X is the size that we're cutting. We're cutting those sides out. So the volume would be length times width times height. Volume is length times width times height. And this width here, if this is 18 inches from side to side, and we cut out an X here, and we cut out an X here, then that width is 18 minus 2X. So I already know that I have the height. The height is X. We could call this the height. So I have a height, that's X, and I have a width, that's 18 minus 2X. And then we have the length going this way. That sheet metal is 30 inches, or yes, inches. That sheet metal is 30 inches long, and we're cutting out an X here and an X here. So we have 30 minus 2X for that dimension. Well, can't make it do what I want. Okay. 30 minus 2X. So we're going to put that there, turn it sideways for the length. So 30 minus 2X. And if we go over to our calculator, we can have the calculator expand that for us. Nope, not there. Using algebra, we can expand for X times 18 minus 2X times 30 minus 2X, and get that polynomial for the volume. So the volume, whoop, went too fast. The volume in terms of X is 4X cubed, 96X squared, 540X. So volume in terms of X is 4X cubed, 96X squared, and 540X. We need the derivative. So first we set up the equation. We know what it's going to look like. And we need the derivative with the critical numbers. 12x squared minus 192x plus 540. Let's factor out a 12. I believe each one of those is divisible by 12. That's not so pretty. So there's no factors of 45 that add up to 16 that I can think of in the top of my head. So I tell you what, we will complete the square. How about that? So I'm going to move the 45 out to the side and think about half of 16 is 8. 8 squared is 64. So we can add and subtract 64 on the same side of the equation and keep that balanced and solve this way. So we have x minus 8 quantity squared let's see, that's minus 19. So how about we move the 19 over to the right, take the square root of both sides, square root of this side, and the plus or minus square root of 19 gives us x minus 8 plus or minus radical 19. So x is 8 plus the square root of 19, or x is 8 minus the square root of 19. Now that leads me to think about the domain here a second. Let's go back to the picture. Then talk about the domain. So in the instance of domain in this situation, if I fold sheet metal straight down the middle at 9 inches here and 9 inches here, if we cut out a 9-inch square, there is nothing left to make a box from. So that lets me know that my x values have to be somewhere between 0 and 9. So we want to check which one of these, or do both of these, make valid solutions. So we can check 8 plus the square root of 19. That answer would be fold up sides that are, whoa, how big? 12.358. Well, that won't work. So we can't have 12.358 sides. Must be the other one. So 8 minus the square root of 19. Whoop, what happened? Oh, 8, 8 minus the square root of 19. And that side is 8. Nope. Oh, mercy. I really messed that up. 8 minus the square root of 19. Why is it not doing that? 19. Gotcha. Okay, that's better. 3.6411. So this one's better. 3.6411. So about that much, because this one doesn't work. So we're going to use that. And we know if x is about, well, we know exactly actually. So we know that the measurement has to be 8 minus square root of 19. And if we go back to the volume equation, which was where? Volume. I'm going to copy that, put that in the graph window, solve that. And we want to evaluate, I want to evaluate that graph at 8 minus radical, 19. Well, that keeps jumping out of the radical mark, doesn't it? 1.9 decimal. So our volume is 886.553. So the volume is about 886.553 cubic inches. And we know, let's answer the question now. What size squares should be cut to make a box of maximum volume? What is the volume? So we could put all that together in one complete sentence. Something like the volume of approximately 886.553 cubic inches will be maximized by cutting squares. That measure eight minus the square root of 19 inches. And the reason we know that is because the derivative was 0 at 3.641 inches, which is this amount. And the signs changed from positive to negative, even though I didn't run that test. We know that's going to happen. Signs change from positive to negative here. Whew, that was a big one. Okay, what's next? Let's see. So in the last few examples, we were guaranteed that the functions had absolute extrema. And what happens if the domain is neither closed nor bounded? Here's a little 9-step strategy I'll save for you to read on your own. And we want to know, what are the dimensions of an aluminum can that can hold 40 cubic inches of soda and uses the least amount of aluminum? So we want to know, let's see what's going on here. Oh yeah, this is how to find the area. We'll use that in a minute. So first of all, we know that the surface area, that's what this picture is going to help us. You see how there's a circle up here and a circle down here? So we have a circle at the top and a circle at the bottom. We have 2 pi r squareds. And what happens when you take that can, remove all the pieces, see how the side that's the cylinder, the circumference of a circle is 2 pi r. So we have the circumference times the height there. This piece flattens out and makes a rectangle. The area is 2 pi r h. So that's how we're getting the surface area. So 2 pi r h. What else did they tell us? Volume is 40 cubic inches. Pi r squared h is 40. And how did we know that? Because volume is the big base times the height. Volume is big base times the height. This base is pi r squared. So the area of the base times the height gives me volume. And height is 40 divided by pi r squared h. So we know about surface area. The domain has to be positive, and the volume is 40 cubic inches, right? We know those things related to our problem. Now, secondly, I want to write surface area. And what are we looking for? Let's read it one more time. It's capped at both ends. So let's say we wrote surface area in terms of the radius, because we could rewrite and eliminate height if we just had surface area in terms of the radius, because we had 2 pi r squared plus 2 pi r h, and I want to get rid of that h and put this expression in there. So surface area is 2 pi r squared plus 2 pi r times 40 divided by pi r squared. Whoa, back up. H. I didn't want to do that. Are you yelling at me? Okay. So simplifying that surface area in terms of the radius would be 2 pi r squared, and pi r would cancel and leave us 1 r down here. So 2 times 40 would be 80, and we would have r to the negative 1. I'm going to write it that way so we can take a derivative. So next we want to find where is the surface area derivative 0. We need to know that to get a critical number. So the surface area derivative is 4 pi r minus 80 divided by r squared. So setting that equal to 0, we want to know where is that 0. 4 pi r is 80 over r squared, which gives us r cubed. So collect r's over here. And 80 divided by 4 pi is the cube root. So our r is the cube root. Uh-oh, that's not good. My pen gets crazy here. Okay, go back and do that again. Is the cube root of 20 divided by pi, and the cube root of 20 divided by pi is going to be that expression, the cube root 20 decimal divided by pi. 1.85336. Okay, so we have 1.85336 inches. The radius is that much in inches. Now, remember how I said that we don't have to do the sign chart because it's always going to come out, but I'll just show you anyway. So if we have 1.853 and substitute back into our derivative some values smaller between 0 and 1.8 and then larger, this is our derivative. So you can tell that the 1.85 is a minimum there. Excuse me. And then we can answer the question. So the can would measure, is this a soda can? Just an aluminum can. Oh, soda. The can measures a radius of 1.85 inches. It has a height. You have to go back and substitute for height in here. So we want 40 over pi r squared. Now, the calculator is going to turn it to a decimal. So 40 divided by pi, and the radius was 1.85336. Whoop, I missed the square. Let's copy that. Paste that. And go downstairs and look. square, the last term, 40 over pi r squared, 3.7067. 3.7067. 3.7067 inches. With a volume of 40 cubic inches, because that was given to us. Okay? And then if we needed to, we could justify the reason why. Because the derivative was 0, and the derivative changed signs from negative to positive at that 1.853. Okay, in this case, a little algebraic type. Which points on the graph of the parabola 4 minus x squared are closest to the point 0, 2? So this is a minimum problem. We're looking for a minimum distance. Okay, and by the distance formula, whoop, I don't know what happened there. Oh, by the distance formula, well, what happened? Not going anywhere. So we'll say by the distance formula, we know the distance is, let's see, here's 0, 2, and we're going to pick some arbitrary point, right? The shortest distance. We'll call that an x and a y. So using the distance formula, we could say x minus 0 and y minus 2 and y minus 2. We're going to go back and substitute that y. So expand all of that. The distance is x minus 0 squared and y minus 2 squared. Let's see, what would that be? 2 minus x squared squared. So this would turn out, let's expand that out. This would be x squared and 4 minus 4x squared plus x to the 4th. Okay, so combining like terms, our distance is x to the 4th minus 3x squared plus 4. Now, here's an interesting little fact. The radicand is really sufficient for finding the smallest critical value because it's going to be in the derivative. The radicand is, make a little note about that. The radicand is sufficient for finding the smallest critical value. So let's find the derivative of just the inside piece. We'll give it a different name, call it g of x. So here on my calculator, you notice how I've taken the derivative of the function itself, put the square root, the entire square root using the distance formula into the graph. And on the scratch pad, I took the derivative. This is the reason I said that the radicand is sufficient, because it's down here in the denominator. And if we find the values that make that radicand 0, then we've taken care of the part that's going to solve for the shortest distance, because the derivative of the radicand is also in the numerator, if that makes sense to you. Okay, so here we go. If I, like I said, if I rename the radicand and call it g of x, take the derivative, factor out a 2x, find the critical numbers of the radicand, then we can test these. With the test strip. First derivative test. So what's happening is if we have negative square root of 1.5, 0, or positive square root of 1.5, and I'm substituting numbers in back here, so we get negative, positive, negative, positive, for some number in between each interval. We have a minimum here, and a maximum here, and a minimum here. So we're looking for minimizing. We want the shortest distance. We want a minimum. Okay, so what does that tell us? And again, I'm going to go back to my calculator step. So we know that the f of positive square root of 3 over 2 and the f of negative square root of 3 over 2, let's see what those would be. So I want to evaluate the square root. Well, evaluate the square root of 1.5. Well, I'm just having a real hard time with the square root function on this calculator. Okay, 1.3, whoop, is 1.322. Oh, wait a minute. We want 4 minus, hold on. I want the f of that. I left off the 4. It's 4 minus x squared. So it doesn't matter whether I do plus or minus. When we square the negative, it's still going to be positive. So 4 minus root 3 over 2 quantity squared. 4 minus square root, oh wait, 3 over 2 squared is going to be 3 over 2. Uh-oh. Squared. So 2.5. That's 2.5. So the closest points, we could do the second derivative test. Let's say by the second derivative test. So we can use the second derivative test to find a maximum and a minimum. The second derivative is going to be positive for those two values. Let's go back and look at our first derivative. First derivative was 4x cubed minus 6x. Second derivative would be 12x squared minus 6. So 12 times 3 over 2 minus 6 is going to be positive no matter what. That means the closest points to our target number, 0, 2, on the graph of the parabola, are negative square root of 3 over 2, 2.5, and positive square root of 3 over 2, 2.5. Let's see where that looks like. If you come over here, 1, 2.5. So right about in there. And 1, 2.5, right about in there. This is the first one. That's the second one. All right, that one was crazy. Okay, got a couple more. So again, some methods for reading that I'll save for you. And here goes a shortest distance problem. This is a real problem in business and industry. Let's read the question. The training facility for a sports club is situated along a straight shoreline. You row your kayak out 2 miles from the nearest point on the shoreline and then row 6 miles down the beach each day to train for an event that includes rowing and running. If you can run at a rate of 3 miles per hour and jog at a rate of 5 miles per hour, what's the least, if you can row at a rate of 3 miles per hour and run or jog at a rate of 5 miles per hour, we want the least or minimum amount of time required to reach the clubhouse. So how far from the clubhouse should you beach your kayak? That's the question. Where is that? So let's call this X. You go down 6 miles, you row out 2 miles, and you row back, and then you're going to jog this distance. Well, this distance is 6 minus X. And our domain has to be somewhere between 0 and 6. Can't be outside of that. What did they tell us? We can row at a rate of 3 miles per hour, and we're going to jog at a rate of 5 miles per hour. And our most famous formula, distance is rate times time. Distance is rate times time. So the time is the row time plus the jog time. If we figure those things out, we have it done. Okay? So the total time in terms of X would be, let's look at the picture. Let's see, what do we know? 2 squared plus X squared is the hypotenuse, right? X squared plus 4. So we have the square root of X squared plus 4 is our rate for distance over time, for the rowing distance over time. And our jogging is distance over jogging time. And putting that all together, we're going to take a derivative. So the derivative in terms of X is 2x over 6 square roots of x squared plus 4. And this is going to turn out to be 1 over 5, because I got 6 over 5 is 0, and negative 1 over 5 is 1 over 5. And this one I just kind of rewrote it, did it in my head. Actually, I cheated on the calculator. That's got a 3 there. And we want to know, when is that derivative 0? So the derivative is 0. When does that happen? Because that's our critical numbers. So we have what? X over 3 square roots of x squared plus 4 is equal to 1 over 5. And solving for x, we have 5x is 3. Well, we could leave the 3 there. Yeah, I don't know. Let's take it over here. Okay, and then we're going to square both sides to get rid of the radical. So 25x squared is equal to 9 times x squared plus 4. And that's 25 minus 9x squared, so 16x squared. 9 times 4 is 36. And x squared is 36 over 16. So x is plus or minus 9 over 4. Let's see, right? 9 over 4. And the square root of 9 is 3, and the square root of 4 is 2. So a mile and a half. And we can't have a negative. We only want a positive domain, a mile and a half. So when the time, we want to stop right here at a mile and a half. So what's the time at 1.5? Well, time was 1.5 squared plus 4 over 3 plus 6 minus 1.5 over 5. And the time is 26 over 15 hours. I'm going to ask you to trust me since I'm 47 minutes into this lesson. So the least amount of time, the least amount of time, t at 3.5, is about 1.73 repeating hours. If you beach the kayak, at a mile and a half. And the reason we know that is because the derivative at 3 over 2 changes signs from negative to positive at that place. We have one more example. So, you know, just in case, I think I used to date him. He found a 4-foot piece of wire left on a construction site. He's learning about optimization and calculus, and he wants to cut the wire to create a circle and a square. We want to know how much of the wire should be used for each shape in order to maximize the total area. This is a common problem here. You see this in lots of textbooks. So the total area is the area of the circle and the area of the square. And we know the circle area is pi r squared. We know the circumference is 2 pi r. And the square area is side squared, and the distance around is perimeter for 4 times the side. So first of all, if we have a piece of wire with, let's see, the total area would be pi r squared plus s squared. And we have a 4-foot piece of wire, 4 feet of wire. So either 4 is the circle circumference plus the square perimeter. The circle circumference plus the square perimeter. So together they make 4. And we want to talk about the domain. So the domain would have to be somewhere between 0 and 1, since the side has to be between 0 and 1. And the area of the circle is the radius. Let's see, hold on here a minute. Okay, so if we had the 4 feet of wire and you had a square, it would be 1, 2, 3, 4. So that's why our side has to be somewhere between 0 and 1. And the area of the circle would be, what, r is 2 over pi. The radius would be 2 over pi. And the area would be 2 over pi. So 2, let's see, let's do that with the calculator. So if area is pi r squared and our radius is 2 over pi, then the area would be 1.273. Put a little star by that. I'm going to need that in a minute. And we can think about this area here. The area is 4 is 2 pi r plus 4s, or the circumference. 4 is the circle circumference plus the square perimeter. We're looking across this line here. All of this stuff in here. So 4 minus 4s divided by 2 pi would give us a radius, and we could reduce this down to be radius is 2 minus 2s over pi. So solving for r, this is going to be my substitute. So here we go. We're going to look for an area in terms of the side. So we have pi r squared plus s squared. And area in terms of the side is going to be pi, this is my substitute, over here, r 2 minus 2s divided by pi squared plus side squared. The area for the side in terms of side is pi, and then expanding all of this out, we've got 4 minus 8s plus 4s squared over pi squared plus s squared. And this pi would take away one of those pi's, and if we gave the side squared a pi over a pi, we could get a common denominator, rewrite the entire thing as, let's see, I'm going to pull out the 1 over pi common denominator here and here. 4 minus 8s plus 4s squared plus pi s squared. And what do we got? We could add these. We could add these together. 1 over pi is 4 plus pi s squared minus 8s plus 4. And then take the derivative. Ooh, this is a long problem. So a prime of s is 1 over pi, and this would be 2s, 4 plus pi to the first power, minus 8. Derivative of 4 is 0. And we want to know, when is this equal to 0? So in the numerator, when 2s times 4 plus pi equals 8, I added 8 to that side. We could divide by 2 when 4 plus pi s is 8 divided by 2 is 4. So when the side is 4 plus 4 plus pi, let's go to the calculator. So clear that out. 4 in the numerator, 4 plus pi in the denominator, 56009. So when side is 56009. So by the first derivative test, that should be a 0. A prime. That should be a minimum, I mean, 0.560. And we're going to make a minimum happen. Where's my thing I put a star by? The A of 0 is 1.273. The A of 2 over pi is 1.273. The A of 0.560 is 0.560. And the A of 1 is 1. So if it was the square, if the length of the square is 0, the area is maximized. Oh, I messed up here. If the length of the square is 0, the area is maximized. Whoop. That's this one. The area is going to be maximized if Justin uses all of the wire to make a circle, because that's an endpoint maximum. Justin should use all of the wire to make a circle. This is an end point maximum. Don't make a square, just make a circle. We're finished with chapter 5.